Hey guys, in this video we are going to talk about our first two classifications of intermolecular forces, namely the charge-charge and dipole-dipole interactions. We're going to start off with a discussion of basically what these different types of intermolecular forces are, where they come from, talk about their relative strengths, and then we're also going to spend some time looking at different applications of these types of intermolecular forces, and we're going to spend a fair amount of time talking about some biochemical applications. For example, the ion channel that I have illustrated here on the cover slide. So as I said, these first two types of intermolecular forces very much build upon concepts that we've talked about before in the course. So we're going to start our discussion with charge-charge interaction and then move into a discussion of dipole-dipole. So first up here, charge-charge interactions. As I said in the introductory slides, this is something that we are all very familiar with at this point, right? When you have charged particles, charged ions, charged atoms, right? These atoms and molecules will interact with one another according to Coulomb's law. So for example, if you have a positive charge and a positive charge, then those two positive charges are going to repel. They're going to be moving in opposite directions. There's going to be a force exerted in opposite directions, pushing these two positively charged particles away, and the magnitude of that force is equal to this product of the charges divided by the square of the distance. And remember that distance here, r, is simply the distance, typically measured in meters, that represents the distance between those two charges. And similarly, if you have two charges, but this time they're of opposite signs, then you're going to see if the charges are the same magnitude, a same magnitude force, but now the force is going to be attractive, pulling those two charges together. And so what we found in building ionic compounds earlier in the course is that ionic compounds will form when you have negatively and positively charged ions coming together. And these ions will arrange themselves in specific configurations, for example, sodium chloride, illustrated here. And these alternate positive, negative charge lattice structures, as they're called, that are built up, have very strong intermolecular interactions. So these charge-charge intermolecular interactions are very strong. And in fact, they're on the order of about 1,000 kilojoules per mole. So to give you guys a little context, if we're talking about a covalent bond, right? So covalent bonds, well, there's a broad spectrum depending on the specific type of bond, right? But you can capture a vast majority of single covalent bonds, with the values of about 150 to 400 kilojoules per mole. So certainly the ionic bonds are oftentimes weaker than covalent bonds, but they're still very strong. And in fact, these ionic bonding interactions really serve as a driving force in a wide variety of different interesting chemistry applications. A couple that I find particularly interesting are looking at biomolecules and looking at how charges in biomolecules dictate the structure and function of these molecules. So many of you guys, no doubt at this point in your education, have seen DNA, the double helix of the DNA molecule. And so we've got a double helix illustrated right here in the gray. Okay, if we unwind that double helix and look at sort of the backbone of that DNA molecule, what we find illustrated right here are these groups where we have phosphates, right? These little phosphate groups that kind of line the whole background, and then these are A's and T's, C's and G's, the base pairs right here, okay? And if you look closely at these phosphate groups that are linking together the strand of DNA, a single strand of DNA that then pairs with its complementary strand on the other side, that single strand of DNA is held together by these phosphate groups that all have a negative charge on them, all right? So the DNA molecule naturally has a negative charge, right? It's an ionic compound, okay? And so this negatively charged aspect of the DNA molecule has a big impact on many different facets of DNA function. one of the particularly interesting ones, I think, is how that DNA is actually stored inside the nucleus of the cell. Because there's so much negative charge there, a couple things happen. One, there's oftentimes positively charged ions, magnesium, for example, that gets associated with the DNA, right? But also, when you're storing that DNA in the cell, that DNA is not stored in isolation. It's actually wrapped up around other proteins. So I'll kind of highlight the protein molecule here on the interior here. Highlight it as a protein molecule. It's a specific type of protein. It's called a histone protein, okay, histone. And these histone proteins basically have a bunch of positive charges around their outside, and those positive charges interact with the negative charges that we just saw on the DNA, right, by virtue of these strong charge-charge interactions, and it basically serves to hold that DNA on there, wrap up that DNA nice and tight in these loops. And these looped up DNA structures around histone proteins are actually the major form in which you find DNA inside of the cell. Okay, another really cool example of charge-charge interactions, and this is the one that was illustrated on that cover slide of our little talk here, is this idea of ion channels. Right? And now ion channels are basically little conduits in cell membranes, right? We know that our whole body is made up of cells, and the outer portion of that cell, called the cell membrane, has different proteins embedded in it that are designed for a variety of different purposes. One of those purposes is the transport of ions. And this is of particular interest when you're looking at nervous system tissue. So if you consider the human brain and the structure of the human brain, well, it's this whole network of these cells called neurons. Okay, so you have trillions of these neurons all coming together, all communicating with one another. Well, the action of neurons themselves actually depends upon the movement of specific types of ions across the cell membrane. So this could be, for example, the outside of the cell, right? So this could be like inside or outside, doesn't really matter, right? Inside and outside, and then we have this membrane, the cell membrane, separating these two spaces. In order to get ions to move through that membrane, you need to have a specific structure, which is called an ion channel. And these ion channels are proteins, so we see a little zoomed in image of right here, proteins that basically arrange a bunch of charged amino acid groups in just the right configuration to allow the selective passage of only certain types of ions. Okay? Really fascinating chemistry, again, based upon charge-charge interaction, right? So if you really want to understand how the human brain works, it actually is boiling down in part to this idea of charge-charge interactions and ion channels, right? Then building those sort of core components of nervous system tissue. Okay, so what I hope you're getting a flavor for here is that charge-charge interactions, well, they're very simple, right? They're also very important. They show up all over the place. Okay, so now let's go ahead and move on to our next set of interactions, the so-called dipole-dipole interactions. Now, remember, in order to understand dipole-dipole interactions, we have to step back and do a quick recap of the different types of covalent bonds. Okay, so remember that we basically had two broad categories of covalent bonds. We had so-called polar and nonpolar covalent bonds. And we were able to basically classify these two different types of covalent bonds based on the relative affinity for electrons of the two atoms involved in the bond. So we had this sort of loose rule of thumb that said that if the difference in electronegativity, which we denote delta En, is greater than about 0.5, right, then you're going to have a polar covalent bond. If you don't meet that classification, if it's less than that 0.5 cutoff, then we're looking at a nonpolar bond. So for example, if you're looking at two hydrogen atoms, playing tug of war with those electrons there, sharing those electrons, well, they're both just about equal strength. They have and in fact, because they're the same exact element, right? So by definition of electronegativity, the difference in electronegativity is zero, and so the resulting covalent bond is nonpolar. Now, if you take two elements of differing electronegativity, for example, chlorine and hydrogen, right? And you look up on that electronegativity table and you find their delta, the difference in electronegativity is 0.9. Well, this is above that 0.5 cutoff, and so we're going to be classifying this covalent bond as a polar covalent bond. Okay, now remember, we took this a step further, right? We said that, okay, if you have a polar covalent bond, then what that essentially represents is an asymmetry in the distribution of electrons, right? So in other words, the chlorine atom here is going to be pulling those electrons closer to itself than the hydrogen, okay? So there's going to be more electron density centered around that chlorine atom. So to draw this out on from a molecular standpoint, we do two different things, right? First, we could think of the molecular orbital that describes the electron density that I'm kind of outlining right here. This molecular orbital is going to show a greater electron density around that chlorine atom over here on the left-hand side, okay, as illustrated, okay? And so that gives rise to a partial negative charge on that more electronegative chlorine atom and a partial positive charge on the more electropositive hydrogen atom, right? When you have this separation of charge, that is what gives rise to a dipole moment. Okay, and remember, we represented these dipole moments by this little arrow, and we put this little plus, the cross sign, on the electropositive element. And basically, this dipole moment is simply a vector quantity that occurs anytime there is a separation of positive and negative charges, right? And what these dipole moments do is they basically give us a way to mathematically quantify the concept of bond polarity, because we can now talk about the direction in which that the asymmetry in the electron density is shifted, and we can talk about the magnitude of the shift. How big that dipole moment is going to depend on how big the difference in electronegativity between the two elements. So now, based on this concept of the dipole moment for a given bond, we can then talk about molecular dipole moments or net dipole moments. So simply put, the net dipole moment for a molecule simply represents the vector sum of all of the dipole moments associated with the polar covalent bonds. So in other words, I could have, for example, CO2, which has a very prominent dipole moment associated with each one of those carbon-oxygen bonds. However, now because these two dipole moments are oriented in opposite directions and pulling with equal magnitude, what effectively happens is that these dipole moments actually cancel each other out, and the result is that you have a zero net dipole moment. So overall, you have a nonpolar molecule, right? Now conversely, if you have a different molecular geometry, so for example, in the water molecule here, where you have two dipole moments, but now these dipole moments are oriented at an angle, the result is a molecular dipole moment that is non-zero, and you'll of course then end up with a polar molecule, okay? All right, and so we did this before. We played this game, we looked at the different geometries, and we basically came up with a method for identifying non-zero dipole moments, right? And so there's really two criteria that must be met in order for a molecule to be polar, right? There must, of course, be polar bonds. Polar bonds are a necessary but not sufficient condition for the existence of a net dipole moment. So if you have those polar bonds, the next thing you do then is look at the geometric arrangement of these atoms in the molecule. And so we found that if you have equivalent polar bonds and they're arranged either in a linear configuration as you see here, trigonal planar, or tetrahedral geometry, then the result will be a cancellation in that dipole moment, okay? And hence, a zero net dipole, right? So in other words, a nonpolar molecule. Okay, so that ends our little recap here. So now the question is, okay, so why do we care, right? We remind ourselves we can identify whether or not a molecule is polar or nonpolar, but what's the application? Well, remember, once you have a net dipole moment, then two different molecules with their net dipole moments can interact with one another, and they will. And this interaction between two dipole moments is called dipole-dipole attraction. And again, we're talking basic concepts from electrostatics here, right? If you have a positive, negative dipole moment here, positive, negative dipole moment here, right? Then the negative part of one dipole moment will want to align itself so that it's close to the positive portion of the adjacent dipole moment. You could do this in a head-on fashion, or you could do this in a side-to-side fashion, as we're illustrating here on the right-hand side, where the negative of the first dipole is close to the positive of the second, and that positive of the first is also close to the negative of the second. Okay, so either of these arrangements or any variations thereupon are examples of dipole-dipole attraction. Okay, so if we consider the energetics of these interactions here, we talked about charge-charge interactions. These are relatively strong. Well, the dipole-dipole interactions, remember the dipole moment isn't a formal charge. It's a separation of charge. And so then it's perhaps not surprising to learn that the magnitude of those interactions are almost an order of magnitude lower than energetically speaking than those of the charge-charge interactions. So, polar compounds, if you have a polar compound, you can think of dipole-dipole interactions as typically ranging between 10 to 20 kilojoules per mole compared to the 100 kilojoules per mole for charge-charge interactions. Now remember, these numerical values are very much approximate. You're always going to be able to find outliers. My goal in this introductory presentation will just be give you guys a ballpark idea of the relative rankings in terms of energetics. All right, and so there's many things that will actually influence these numbers. So for example, the magnitude of the charges, right? Higher magnitude charge, stronger interaction. The separation distance between the charges, if the charges are further apart from one another. Remember, we have this relationship, the inverse square law, Coulomb's law, which tells us as this distance r gets higher, then the energy is going to become less. And of course, the orientation of dipole moments is going to be important. In fact, if we have a dipole moments that are head-on, but with the negative charges together, you'd actually get a repulsive interaction. So molecules are going to preferentially orient themselves to have favorable attractive forces between their dipole moments. And then other factors even beyond that come into play. For example, the surrounding environment, the electrical properties of the medium in which the charges or dipoles are found can have a very significant impact on the strength of interactions. All right, so we're not going to go into much more detail on this right now. I just sort of want you guys to file away this idea that there are many factors that contribute to this energetic. So the ranking games that we're going to be playing in our introductory discussion here are very much approximate. Okay, and so with that, we're ready to go ahead and move on to our next intermolecular force, which is hydrogen bonding, in the next video.